Hi, I'm Mrs. Edwards, and today we're going to be looking at polynomials, and we want to observe some patterns in end behavior, and there's zeros, and then the patterns in those zeros or x-intercepts of the polynomials, that's known as multiplicity. We'll put it all together and be able to make sketches of these polynomials. Let's just start here with this f of x equals a fourth degree polynomial. If I go to graph this particular polynomial, and I just went over to Desmos.com and graphed that, I want you to notice that it comes down and it comes in contact with the x-axis here at 3 and then goes back up. So the zero of this function is 3. Zeros, it's just another word for x-intercept. And so the reason why it's called a zero is if I were to substitute the number 3 into this function, 3 to the fourth minus 12 times 3 to the third plus 54, 3 to the second minus 108 times 3 plus 81, that's going to equal 0. So it's the number that makes the function equal 0. But then that also means it is an x-intercept. So vocabulary, zeros of a function and x-intercepts, those are interchangeable here in this instance. And then if we factor, well, x minus the x-intercept is a factor of the original function. So since 3 is an x-intercept, we know x minus 3 is a factor of this function f of x. Now also, we can write functions as x minus a number times x minus a number, and we have as many of those as we do the degree of the polynomial. So in this case, the degree of the polynomial is 4. Now, it doesn't mean for sure that they are all x minus 3. We could have some imaginary roots, but in this particular case, the exponent on x minus 3 is to the fourth power. If you multiplied x minus 3 times x minus 3 times x minus 3 times x minus 3, you would have this function right here. That brings us to what is multiplicity. So multiplicity is how many times you see that factor that leads to an x-intercept, in this case, of 3. So x minus 3 shows up as a factor 4 separate times. And so that means that this 0, which is 3, has a multiplicity of 4. The significance graphically of multiplicity, it tells you the behavior of the function at that x-intercept. The graph is either going to slice through the x-axis at that x-intercept, like here maybe the graph goes through 3, 0 and keeps on going down, that would be a slice, or the graph bounces off the x-axis at that x-intercept, which is what happened here. The graph comes down, comes in contact with the x-axis, and then goes back up again. That is always going to happen when you have an even multiplicity. So since x minus 3 showed up 4 times, the number 3 has a multiplicity of 4. Since it's even, the graph bounced off at 3. So you want to write that in your notes. If you have an odd multiplicity, then the graph will slice through the x-axis. And if you have an even multiplicity, it's going to bounce off the x-axis. Okay, next what we want to talk about is the end behavior. We want to look for some patterns on, does the graph eventually both go up, like in this instance here, eventually they both go up, or maybe you have one up, one down. And let's take a look at some examples to observe some patterns. We're going to look at the graphs of these 4 functions and make some observations. But before we even look at the graphs, let's make some observations about these equations. Notice that this r of x is degree 3, g of x is degree 5, b of x is degree 3, and p of x is degree 7. All of these have an odd degree. Then The leading coefficient on the functions on the left, positive 2 and positive 1, those are positive, and on the right, the leading coefficients are negative, negative 1 and negative 0.5. So let's see if we can notice anything. All right, we have all 4 graphs now. See how all of them have that basic shape. On the end, one goes up and one goes down, depending on the graph, but we have one side is up and one side is down. That general shape is preserved. So what is making that general shape? Okay, this curve that looks like this, whether it's going up or going down, that's because it's an odd degree. The higher the odd degree, like x to the third, x to the fifth, x to the seventh, polynomials that have a higher odd degree, they still have that basic shape. The only difference is that you might have a couple extra bumps in the middle before it takes off. That usually happens like if I had x to the fifth and I put in several other terms like x to the fifth plus 3x to the fourth plus 2x to the third minus 7x plus 4. Well, it's still going to have this basic shape. We just might have a few extra little bumps in the middle before it heads up. Okay, then the other thing is notice these ones here on the left having a positive number in front, the leading coefficient's positive, and as your eyes hit it, your eyes go up. You can read a graph just like you read a book. Your eyes go from left to right. So notice as my eyes move from left to right on this R of X graph, when my eyes come across, I hit the graph, and if I follow the graph, my eyes go up. Positive leading coefficient. Okay, here, positive 1. Notice my eyes hit the graph looking from left to right, and then my eyes go up. All right, when I go to B of X, if I read the graph from left to right, I look across until I hit the graph, and then my eyes go down. So that means that I have a negative leading coefficient, and the same thing here. I go across, my eyes hit it, and my eyes go down, so I have a negative leading coefficient. Okay, so the takeaway here that you want to write down so far is that if you have an odd degree, that your graph is going to be one side up, one side down. And if you have a positive leading coefficient, then it's going to start down and go up. If you have a negative leading coefficient, it's going to start up and then go down. Here we have 4 more functions, but notice this time all of them have an even power, 2, 4, 4, 6. So we have even degree, and then sometimes the leading coefficient is positive and sometimes negative. In this case, negative 3 is the leading coefficient, and here, positive 2. Pop in those graphs, okay, and you notice that basic shape. Whenever we have an even degree polynomial, then it's either going to eventually go both up or both down. This one is easy as well because you've got negative just means frown, and if you have a positive, it's going to smile. All right, and then just a couple more notes about that is that if you have more terms, like let's say you have a 2x to the 6th, but we throw in plus 5x to the 4th minus 3x plus 2x minus 1. The only thing that's going to happen is you're going to get a few more bumps in the middle, but otherwise you're going to have them still both going up on the ends. So please make sure you put that in your notes. Even degree polynomials, either both up or both down. And it's both up if the lead coefficient is positive, like this one, and both down if the lead coefficient is negative. Let's just see if you have this down. No pun intended. All right, so let's start here. What's the graph going to look like? hopefully you knew that it was going to be one side up, one side down, because it's an odd degree, and then a negative in the front means when my eyes hit it, my eyes are going to go down. So here's my basic shape. Okay, then, all right, see, x squared, you're either, because you have an even degree, they're either both up or both down, and because we have a negative coefficient in the front, they're going to be both down. So our basic shape will be down. How about this one here, the 3x to the 4th? Yep, both up, because we have a positive telling us both up, an even degree, so they're either both up or both down. Okay, last one, just to test your understanding. What's that graph shape gonna look like? Yes, one up, one down. We have an odd degree, so one up, one down, and then the number in front is a positive, and so as our eyes hit it, our eyes go up. Now we're going to formalize this end behavior. There's some notation that is likely new to you that describes the end behavior. Say we have a polynomial f of x equals a sub n x to the n. So in other words, a sub n is representing the leading coefficient, and then n is the exponent. So in this particular example, the lead coefficient is positive, and the exponent is even. Okay, from our examples that we just looked at, hopefully you now know an even exponent means either both up or both down. Because we have a positive in the front, they should be both up. But we've got some notation that describes this end behavior that we're going to talk through. So I'm just putting an example where the leading coefficient is positive and the exponent is even. Okay, and then verbally, as I move to the left, we're going up, but the notation for that is the limit as x approaches negative infinity of the function f of x is positive infinity. I tried to color code this to help you with what matches. The limit as x approaches negative infinity means we're going left. Really what it also means is I am substituting in numbers for x into the function. And the numbers that I'm plugging in into the function are numbers that are getting closer and closer to negative infinity. Okay, so for example, if I plug in -1, -2, -3, -4, -5, that is selecting x's heading to negative infinity. And as I substitute in -1, -2, -3, -4, -5, the answers to the function are getting bigger and bigger and bigger, so the answers are heading to infinity. All right, let's take a look at that on the right. You already know verbally that as you move to the right that the function is going up. The notation for that is the limit as x approaches infinity of f of x is positive infinity. Okay, this means as I select numbers to plug into the function, I'm going to start picking numbers that are bigger and bigger and bigger heading to positive infinity. So I substitute 1, 2, 3, 4, 5, 6, and I keep substituting numbers towards infinity. And as I substitute those numbers into this function, the overall answer is getting larger and larger and larger, so the answers are heading to positive infinity. So this is the notation for the end behavior, and we're going to look at this notation for each one of the scenarios to help you get familiar with this notation. Okay, so here we have an example where the polynomial, the leading coefficient is negative and the exponent is even. So hopefully you remember when the even exponent, they're either both up or both down, but because we have a negative leading coefficient, it's going to frown, they're going to both go down. So here's an example of that. And then when we're asked what is the end behavior, and we want to use the notation, when you're saying going left, so as I move to the left, I'm heading down. So that is equivalent to saying the limit as we choose x is heading to negative infinity to plug into the function, our answers are heading to negative infinity. All right, then over here on the right, as I start substituting numbers that are larger, 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 that means I'm heading to the right, and then the answer to the function is going to get lower and lower and lower and lower. It's heading down. So that means, notationally, the limit as x approaches infinity of f of x equals negative infinity. So we're substituting larger and larger numbers by plugging in 1, 2, 3, 4, 5, 6, 7. We are picking numbers to substitute heading to the right. And then the answers to the function, when I substitute those numbers into the function, the overall answer is getting more and more negative, so heading to negative infinity. All right, we're going to go through these ones a little bit quicker. You might want to pause for a second and see if you can answer these ones with a notation. But here I have an example where we have an odd exponent and we have a positive leading coefficient. You know an odd exponent, one up, one down, but because it is a positive in the front, our eyes are going to go up as I move to the right. Okay, so end behavior. As we start moving to the left, we're going down. But the way we say that notationally is the limit as x approaches negative infinity of the function f of x equals negative infinity. Okay, over here, as we move to the right, we're going up. So we're going to say, as we start plugging in numbers towards infinity, the limit as x approaches infinity, we're plugging those into the function. The limit as x goes to infinity of f of x equals positive infinity, because our answers are going to get bigger and bigger the larger and larger x that we substitute in. Okay, here we have one more. An odd exponent, so one up, one down, and a negative, so as our eyes hit this, they go down. So our end behavior here, the end behavior over here on the left side, as we plug in numbers going to negative infinity, and we plug those into the function, we're going to get out answers that are getting larger and larger, so heading to infinity. Over here, the end behavior going to the right. We're heading down, so as I substitute numbers that are larger and larger and larger, our answers are getting more and more negative. So the limit as x approaches infinity of f of x equals negative infinity. Now that we've talked about the end behavior at length, let's go back to the x-intercepts of a function known as the zeros. In this particular example for g of x, we already have it factored, and that's where those zeros stand out. You don't need to expand this any further, but I'm expanding it just so that you can really see what's going on. All right, so the zeros, those are going to be the numbers that make each factor equal 0. And they also are the numbers, if I substitute it back into this function right here, it's going to make it equal 0. So each individual one, x minus 0 set equal to 0 is just 0. Now, how many times did x minus 0 show up? Now, notice it is x minus 0 because I know it's just x up here, but the x-intercept is revealed by x minus the x-intercept. So I just rewrote the x as x minus 0 to emphasize that the 0 is the x-intercept. Okay, so how many times did it show up? Notice it would have shown up twice. So that means that the multiplicity of the x-intercept 0 is 2. All right, then let's look at another one of the zeros of the function. X plus 5 equals 0, solved is x equals negative 5. So negative 5 is an x-intercept, that is a 0 of the function. If I substitute negative 5 back in here, substitute that in, I'm going to get out 0. Now what is the multiplicity of this 0? Well, it showed up once, twice, 3 times. So the multiplicity of negative 5 is 3. Okay, next, x minus 2 creates another one of the zeros, which happens at 2. So what is the multiplicity of the 0, 2? Well, x minus 2 only showed up once. It was only a factor one time, so the multiplicity is 1. Then we have one more 0. If we solve 2x plus 5 equals 0 by subtracting 5 and dividing by 2, we find that we're going to have an x-intercept at negative 5 halves. Negative 5 halves is a 0 of the function g of x, because if I substitute negative 5 halves in for x and simplify, I'm going to get 0. Okay, so 0 and x-intercept, they mean the same thing. Okay, so then what is the multiplicity of the 0, negative 5 halves? Well, 2x plus 5 showed up 1, 2, 3, 4, 5 times. So that means its multiplicity is 5. The significance of the multiplicity is whether or not the function slices through the x-axis at these numbers, 0, negative 5, 2, and negative 5 halves, or does the function bounce off of the x-axis at those numbers. If we have a function factored, we can now make a very, very good sketch of this polynomial, because we now know where the x-intercepts are. Then we can think about end behavior, whether it starts up or down, and whether they're both up or both down. Using those x-intercepts with multiplicity, we're going to make a sketch of the graph. All right, so I brought over the zeros and their multiplicity, and we want to make a sketch of this graph. But we have one more thing before we can do that. We need to determine the degree of this polynomial g of x and the leading coefficient. Of course, we are not going to multiply all of this together to determine the degree and leading coefficient. But what we can do is just multiply all of the fronts here, x, 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 multiply all those together, and that is going to be our leading coefficient. So if I multiply x times x times x times x times x times x times 2x times 2x times 2x times 2x times 2x, that is going to be the term with the highest degree, and we would know the leading coefficient. So ultimately, when we multiply all those together, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the degree is to the 11th. I don't even care what the actual number is. I only care whether the number in front of x to the 11th is positive or negative. So notice positive x times positive x, positive all the way through times positive 2. So our leading coefficient is going to be a positive number. We now know that with an odd degree, we have one side up, one side down. And then since the leading coefficient is positive, that means as we look from left to right, our eyes are going to go up. And so that means we're going to start down and then we're going to head up. Some notation, just to practice that notation. The limit as x goes to negative infinity of f of x means we're substituting in numbers that are more and more negative, so we're heading to the left, and then we're going to go down because we're going to start down and head up. The end behavior, using that limit notation again, the limit as x goes to infinity, so we're moving to the right of the function, and as I plug in numbers, 10, 100, 1,000, a million, a billion, my overall answer is getting bigger, 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 so heading to infinity. All right, so I want a graph, and I've just put in an X and Y axis. I went ahead and already labeled where those x-intercepts are going to be. So let's pop in those x-intercepts. Okay, then the next thing, since we know we're going to start down low and then eventually go up, I want to start the graph down low. And as I go to -5, since the multiplicity is 3, it's an odd multiplicity, so that means at -5, the graph is going to slice through. So slicing through, and then we're going to have to get to this x-intercept, so we're going to have to turn around here, and at -5/2, the multiplicity is 5, so once again we're going to slice through the x-axis at -5/2. So bringing that around, slicing through, and then we're going to have to get to this x-intercept, so we're going to turn this sucker around and head up. However, the multiplicity this time is 2. So since we have an even multiplicity, it means that this function here, it's going to bounce off the x-axis at 0. So since it's going to bounce, I'm turning that around and then bounce and then heading back down again. Lastly, we want to go through 2 on the x-axis, and since the multiplicity is 1, an odd number, the graph is going to slice through at 2, so turning that back around, coming through and slicing, and what do you know? We started down, and eventually as we slice, slice, bounce, slice, we head going up. Okay, so we have the graph of this g of x. What you want to do to have a really nice graph, we're not using a graphing calculator, is you want to know what are the zeros of the function, which was -5, -5/2, 0, 2. Know the multiplicity, and that tells you if you bounce or slice through that number on the x-axis. And then to determine the end behavior, to know whether to start down here or to start up here, we need to know the degree of the polynomial and if the leading coefficient is positive or negative. This time, we are given the zeros of the function, and we want to build our own function that would have these zeros. The solution that we get is not unique. You could have 100 students, and you could have 100 different answers, but I'm going to always build the least complicated one possible, because ultimately I'm going to multiply it all together in the end, and I would like to multiply as little as possible. Okay, so if you're going to build this function, all you have to remember is that x minus the x-intercept, or x minus this 0, is going to be a factor in the function. So for this one, if our zeros are at 2, -3, and 6, I'm going to go x minus 2, x minus -3, and x minus 6. I do need to multiply this together and write my final function in expanded form. So I'm going to FOIL together x minus 2 times x plus 3, first times outer times inner times last, and combine. Next, I need to multiply this trinomial times this binomial. So I'm going to take x times x squared, x times x times -6, and -6 times x squared, -6 times x, and -6 times -6. And I've got that, and combine some like terms, and there is my function. Okay, so let's go ahead and practice making a sketch. If I make this sketch, of course, we have x-intercepts at 2, -3, and 6. Then looking down here, let's think about end behavior. We have a positive 1, and we have an odd degree. So odd degree is 1 up, 1 down. A positive leading coefficient means that our eyes are going to eventually go up. So we're going to be starting down and then heading up. Okay, just practicing notation and behavior. So if we're starting down, that means as we are on the left-hand side, as we choose x's going to -infinity into the function, we're going to be down, so -infinity. And then over here on the right side, we know our eyes are going to go up, so as we choose x's going to infinity, meaning we move to the right, plug those into the function, we're going to go up, so we're going to infinity. Now when I make that sketch there, see how it's sliced? It's sliced and it's sliced, and that's because all of these zeros, 2, -3, and 6, all have a multiplicity of just 1. They all showed up one time. So I started down, slice, 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 and I have my graph. One more time, it is not unique. You could have a student who's like, no, x minus 2. I love x minus 2. Let's make that to the second power. Okay, you can do that. It will change the look of our graph because if x minus 2 is to the second power, then over here at 2, it would have bounced off and then eventually come down. And then you're just going to have to multiply all of that by another x minus 2. So I'm going to leave it with the least amount possible. Somebody else can say, but I love multiplying functions by 10. You go for it. If I throw in a times 10 in the front, it's not going to change my x-intercepts. It is going to stretch this, and that graph is going to have a vertical stretch, but it won't change my x-intercepts. Okay, so one last time, the takeaway is building your function, just do x minus the 0, x minus the 0, x minus the 0. If they tell you that you have to have a multiplicity greater than 1, well then you can go ahead and change these exponents to reflect the multiplicity. One last example of this type. Here we have 3 zeros. I wanted to go with a square root. It's not that much more challenging, but sometimes just seeing a root scares you. So let's have these zeros. X minus each one of these is a factor. So I have x minus root 5, x minus a negative root 5, and x minus 2. I'm going to multiply it together so that I can have my final function in expanded form. So I need to FOIL together these. A shortcut when you are foiling conjugates, these are conjugates, right? They're exactly the same, just one has a minus and the other has a plus. You can skip outer and inner when you multiply because you know those are going to cancel when you multiply conjugates. So x times x is x squared. Root 5x and negative root 5x, those are gone. And then negative root 5 times positive root 5 is negative 5. All right, so we have that, and then we'll FOIL together those, and we have our polynomial. That's what the question asks, but let's just take it one step further to practice the other pieces that we've learned. If we made a sketch, I would just immediately go to root 5, negative root 5, and 2, and put in some x-intercepts. We have an odd degree, so we know that the end behavior is 1 up and 1 down. It's a positive number in the front, so our eyes are eventually going to go up. So if our eyes are going to eventually go up, that means, just again, practicing our notation, as we start off on the left-hand side, as our x's go to negative infinity, plugging those into f of x, we're going to get out negative infinity. So we're going to start low. And then as we move to the right, the limit as x approaches infinity of the function f of x. As we plug in numbers going to the right, we're going to get out bigger and bigger and bigger answers, so positive infinity. All right, so let's make our sketch. We're going to start down here. All of these zeros have a multiplicity of 1 because they only showed up once in our function. And that means it's going to slice. So if I start down here, I'm going to start here. I'm going to go up, slice, come back down, slice, come back up, slice, and head on up. All right, so there is our function.